So we're going to look at work energy problems. Again, the equation is there at the top. T1 plus the work done is equal to T2. And let's look at this problem marked number 1 here. There's a collar that's 5 pounds and it's attached to a cable. And we want to know the force in the cable so that the collar's velocity is 10 feet per second when S is 0. Now, S is starting out to be 8 feet. So let's take a look at this. Now, the 30 degrees really doesn't come into play because remember, if you have a force on a cable and there's no friction involved, the only thing you're looking for is the distance the cable has been pulled. And so let's take a look at that. So again, we have our original position looks something like this. And again, this side is 6 feet according to our picture. And then the bottom, it says S is going to be 8 feet. So there's going to be 8 feet here. So what we can do, we can see what this original length from the pulley to the collar is. And that's going to be 6 squared plus 8 squared. And that's going to be, what do we work in feet? That's going to be 10 feet. So that's going to be the original length from the pulley. And then, of course, the final length from the pulley, it'll be a picture. You don't really have to draw this other picture. It's probably pretty clear what it's going to be. So originally the collar was here. In the final position, the collar is going to be over here. And of course, this distance is 6 feet. So this is the final. And so this one is going to be, so the length of this part of the cable right here, so it's going to be 6 feet from the pulley. And so now we can just put everything into our equation. Again, we want to use work energy. So it's like T1 plus summation U1 to 2 is equal to T2. And again, this is going to be 1/2 MV1 squared. But this is actually going to be 0. And once again, remember, again, for a cable, all we need to do is have the force times the change in the length of the cable. Then the final velocity, mv2 squared. So again, we're going from 10 feet to 6 feet. So the cable changed length. We pulled it a total of 4 feet. And the collar was 5 pounds. And again, since we're in English, we have to divide that by 32.2. And we want the final velocity to be 10 feet per second. like this. And when you put that in your calculator, you get a force of 1.94 pounds, like that. So that's the amount of force that needs to be applied so that when the color gets to this point here, it has a velocity of 10 feet per second. Again, I can't emphasize enough when you have a pulling with a cable and have no friction, all you have to do is figure out how far the cable has been pulled to find the work done from the cable. Next, let's take a look at this problem here. Very similar to the last one. You have a cable pulling. So for the work of the cable, all we have to do is figure out how far the cable has been pulled. Now, notice that, let's see, notice one thing different from the last problem. We also have the work related to the weight, because the weight is being pulled upwards. So we'll have to take that work into account. Now, in this case here, we're told the force on the cable is 300 newtons and terminal velocity when it reaches point B. So let's take a look at this. So once again, we want to find the original length of the cable from the pulley. And so if we look at our picture, we have this distance along the bottom here is going to be 0.2 plus 0.2 is 0.4 meters. And then the length from up here is going to be 0.3 plus 0.2 plus 0.2, and that's going to be 0.7 meters. So again, let's take a look at that, where those came from. So again, the horizontal distance from the pulley down to A was this radius of 200 millimeters, so it'd be 0.2 plus 0.2. Then vertically, we have this 300 plus 200 plus 200. And so we have something like this. And so then the original length is going to be 0.7 squared plus 0.4 squared. And when you put that into your calculator, you get about 0.806 meters. Is it going to be the original length from pulley? And then the final one, the collar gets pulled up quite a ways up to the point B. And so in that case, this is 0.2 meters. This is 0.2. 0.2 squared. 0.2 squared, the square root. And that gives us around 2828. That's the number of meters from pulley. So that's in the final position. So now let's apply work energy. And again, we can just put the equation down, or maybe you want to break it up into different parts. So let's take a look at that. So let's maybe look at the work. Or I don't know, let me maybe look at the kinetic energy first. Let's take a look at that. Kinetic energy 1 at the starting position is going to be 1/2 mv1 squared. Now the original velocity is 0. So that's going to go away. That'll be 0. Kinetic energy 2. T2 1/2 mv2 squared. And that's going to be 1/2 times our 15 kilograms. And we actually don't know what V2 squared is. We just have to put that in for now. And then for the work, so for the work of the cable, that's going to be, of course, our force times the change in length. And we know that the force was 300 on the cable was 300 newtons. And the change in length was 806 was the original length, and 2828 was the final. And when you put that in your calculator, you get around 157. Let me double check that. Times 806 minus 2828. Yeah, around 156.9. Let me round it off to 157 newtons. Or excuse me, Newton meters, I should say, because it's work. And now the work of the weight has risen. And so let's take a look at this, the work of the weight. And of course, remember that is going to be whatever the weight is times the change in height. And what do we have? We have 15 kilograms. But we want it in terms of weight, so it's going to be multiplied by gravity, 9.81. And then when you look at the picture, we have to see how high the weight has been raised. And let's see here. So if you look at the picture at A, it started at A, but then it went up 300 plus 200 equals 500, or 0.5. Then finally, remember, when you do the work energy, if you have to raise the weight, it's going to be negative. So we have to put a negative sign here. So here's our weight. This is how far it moved up, and negative because the weight had to be raised. And when you put that in your calculator, you get 73.6. Newton meters. And I think that's all the work that we have. We don't have any springs, so there's no spring work. So we can just put everything into our equation. Our work energy, T1 summation of the work equal T2. And T1 we determined was 0. Then the work of the cable was 157 Newton meters minus the work done to raise the weight, 73.6. And then our T2 was 1/2 15 velocity squared. And put that in my calculator, got times 2 divided by 15. And so it looks like the velocity squared is around 11.12. And we take the square root of velocity is about 3.33 or 3.34. 3.34 meters per second. So again, in this one, all we had was a cable and we had the weight being raised. Next, let's take a look at this problem. This 2-pound box slides along this smooth circular ramp, and it's starting at 30 feet per second at A. Determine the velocity of the box and normal force on the ramp when the box is at B and when the box is at C. And notice they say the radius of curvature is still 5 all the way around. So let's take a look at this problem. So let's take a look at these one at a time. I'll do the case first when we go from A to B. And the box is coming along the ramp here. And again, we're assuming like this is the vertical direction. So this is going like upward vertically. And so we'll have to set a datum line. Let's call maybe, or well, I don't know if we really need a datum line, but we just need to know how far the box has risen vertically. So let's take a look at the work and the energies. So again, the initial kinetic energy will be T1 1/2 mv1 squared, which is going to be 1/2 to, again, since we're in pounds and we have mass, we'd have to divide by 32.2, and the velocity squared, like this. And this comes out to be 27.95. And that'll be pound feet. And then we have kinetic energy 2, which would be 1/2 mv2 squared. And it's going to be 1/2 2 over 32.2. We don't know what the final velocity is. So that's just going to be 1 divided by 32.2 times V2 squared, like that. And then for the energies, again, there's no spring work, no work of a force. Always think about these. No work from a cable. These are all 0. you don't have to write this down, but always keep these in mind. Always think about, is there a spring work? Is there work from a force? Is there work from a cable? In this case, no, they're all 0, but we do have work from the fact that the elevation has changed. And sometimes we call that the work of the weight. And it went, remember when we're doing work energy for the work, if it has changed in the upward direction, that's going to be negative. So again, negative because it moved vertically upward. And that's going to be 2 pounds. And then the difference in height, it moved up 5 feet, huh? So it's going to be negative 10 pound-foot. So that's all we need. Then let's put it into our equation. T1 summation U 1 to 2 equal T2. And T1 is 27.95. And then the work done was negative 10 pounds and negative 10 pound-feet. And that's equal to 1 over 32.2 velocity 2 squared. And then when you put that in your calculator and take the square root, we get the velocity. And there's a velocity at B. I called it 2 here, B there. You can call it that, whichever you wish. 24.04 feet per second will be the velocity when it gets to B. And now we have to find the normal force that's applied. So let's take a look at that. Let me see if I can put this in here. So here we'll have like a normal reaction here. And notice there's nothing, we have like 2 pounds, but that's going downward. So that's not gonna contribute anything to the normal direction. So let's do F equal MA. And again, I'll call towards the center positive. So we have the normal reaction here. Again, the weight's not contributing anything. And then we have the mass, which is 2 pounds divided by 32.2 feet per second squared. And then the acceleration, remember this is the normal, I'm actually summing in the normal direction. So the normal will be the velocity, excuse me, the acceleration in normal will be the velocity squared divided by rho. And that's going to be 2 pounds divided by 32.2. And we said the velocity at that point was 24.04 squared. And then the radius is always going to be 5 feet. And let's put that in our calculator. And we get something around um, 7.17, 7.18, somewhere around there. Like that. So again, that will be the normal force when the block is at point B, as we're showing up here. And the next part from A to C is very, very similar. Pretty much go through all the same steps. Let me sort of follow the same procedure. We'll do kinetic energy at 1. And now for this, it's best just to go back to A, go back to our starting point, A to C. It's really not very helpful to go from B to C. But just, so if we went to conditions at C, just go back to A and do kinetic energy 1, which is 1/2, and it's same as before, 2 divided by 32.2 times the velocity squared, which is 2795 pound-feet. I ran off the paper a little bit. 27.95 pound-feet. And then kinetic energy 2 is what we don't know. That's going to be at C. Let me just call it C this time. So when I put it in the velocity, so it'll be 1/2 the weight divided by 32.2, and it'll be, I'll just call it V2, V2 squared. So 1/32.2 V2 squared, like this. And then, so we need the work once again. Again, the spring work is 0, no spring, no work from a force, no work from a cable. Those are all 0. And now the work for the weight rising, we have to take that into account. Again, that's going to be the weight times the change in y direction, the vertical direction. Now notice it started down here and ended up here, so it went 5 feet plus 5 feet, so it's going to be 10. And the weight was 2 pounds times 10, which is 20 pound-feet, like that. And let's put everything into our equation. T1 summation U1 to 2, T2, and we have 27.95. And once again, since the weight moved upward, I needed a negative sign here. So let's put our negative sign right there. And so it's going to be, the only work we have is the work of the weight minus 20. And then we have what? 1/32.2 V2 squared, which is at point C. I'm getting like 59, it's going to be 15.99, which is going to be rounded off to 16. feet per second. And so let's take a look at what kind of forces we're going to have. This time it's going to be up at point C. And so now this time, again, the normal force, again, will be pushing down this way, just like before. Now, our weight certainly will contribute. This time, we're going to have 2 pounds in the same direction. And let's sum these up. So sum of force in a normal direction is equal to MA. Once again, we'll go towards the center, will be positive. So let me call that positive, like that. And so we're going to have the NC plus the 2 equal 2 divided by 32.2. And then over here, again, the velocity squared divided by the radius, or divided by rho, which is our radius, which is going to be 2. And so 2 to 32.2. And this is 16. And rho is 5 feet. Like this. And we solve for NC. And when you put all that in your calculator, you get 1.18 pounds of force. So, not surprisingly, the reaction's quite a bit less here, even though the velocity was higher, but because this was pulling in the other direction, the weight, we got that. Let's take a look at this problem. Looks like we have some kind of conveyor belt that's pushing packages off into some kind of an incline. And then the package is sliding down the incline and onto this cart. And we know that we want the velocity when it gets to the cart to be 60 feet per second. So we have to figure out what's going to be the velocity of A to achieve the 60 feet per second when the box gets to the cart. Now, there's going to be a friction along the incline. It's going to slide there and then go from B down to C. Now, this problem we're going to have to do in 2 steps, primarily because here along the incline we have friction, but of course there's no friction between B and C when it's just in the air. So we'll have to do this in 2 parts. And also, since it's asking us for the original velocity, we're going to have to start at C, like at BC, and work backwards. So we have a picture something like this. Again, it's asking for the original velocity, so we're going to have to work backwards. We're going to have to look, say, at B, C, and then kind of work backwards. So again, just focusing from B to C. Once again, let's write our normal stuff. Our kinetic energy at 1. And that'll, let me call that a B. And that'll be like, say, TB 1/2 MVB squared. And we know the box weighs 15 pounds. By 32.2. But we don't know the velocity of B. So we're just going to have to leave leave it like that. So that's a kinetic energy at B. Kinetic energy at C is going to be 1/2 mvc squared. 1/2, once again, 1532.2. And now we do know the velocity at C, that's supposed to be 60 feet per second. So 60 squared. Now for the work, and I forgot to mention on the last part, the other thing we have to consider for work is friction. So, although in this case, between B and C, the friction is 0. And there's no cable and no force being applied. And what other ones did we consider before? Of course, no spring. Again, you don't have to write these down, but always keep these in mind. Do you have any of these? And the answer is no. At least from B to C, there's no friction. There's no force being applied, no cable, no spring. And then now that the only work that we have is due to the height change. So that's going to be the work of the weight times the change in Y. And the work of the weight, again, it's 15 pounds. And now notice the weight goes down. So again, we're doing work energy. The weight goes down, 25 feet, because it started at 30 and it's going to end up at 5 feet. So we have the work of the weight, again, 15 pounds times 30, where it started. It goes down to 5, so it fell a total of 30 minus 5 feet, which is 25 feet is how far it fell. And when we calculate that, that's going to be 375 pound feet. Like this. Now let's put this all into our work energy equation. T1 plus the summation of the work equals T2. In this case, we'll do TB plus the summation of the work equals TC. So again, we substitute all that in, substitute TB into here. We had TB up there. The work we had, all the work was 0 except the work of the weight, which was 375. And then equals TC, which is this. And when you put all this in your calculator, find VB squared, and then take the square root, we end up with 44.6. We can call it maybe 44.61 feet per second. Like that. So that's the velocity at B. And now we're going to have to go back and figure out what the velocity is at A. So we'll have to kind of work backwards to get to that. So now let's look at the next part, the part from A to B. So we have a picture, something like this. It's going down the incline. And now one thing to kind of keep in mind, this is a little bit difficult to see. But if let's say we want to do this, let's say we want to sum the forces in the normal direction, because we want to end up finding NC. we're going to end up having, say, 3, 4, 5, like this. So then when we resolve this in the normal direction, it's going to be 4/5 times 15. And so let's take a look at this. So again, if we want to find the normal, then let's sum the forces in the, say, this normal direction. And let's call this positive. Again, I'm going up in this normal direction. And there's no acceleration in that direction, so just call that the right-hand side 0. So we're going to have our normal minus our 15 pounds. And to get in this normal direction, it'll be 4/5 equals 0. And that's going to give our normal to be 5/3 is going to be 12 pounds. Like that. Then we're going to need our friction force. So our friction is going to oppose the motion. So our friction force, of course, that's always going to be mu times our normal. And our friction force is going to be, and our mu in this case is 0.3. Our normal, we said, was 12. So that's going to be, and that's going to oppose the motion. Well, I'll put it in negative in a minute. I'll leave it positive for the moment. So it's going to be 3.6 pounds, like this. So now let's, so we needed to find all that first, find what the forces are. So once again, think of your kinetic energy. Kinetic energy at A is going to be 1/2 m, which is 15 pounds, divided by 32.2, v at A squared. Our kinetic energy at B is going to be T at B is 1/2 15 32.2. And again, we found that velocity of B is 44.61. Like this. And if we put that in our calculator, times 15 divided by 2, we get TB. This is 463 0.5 pound-feet. And let's see. So let's look at our work now. And again, this time we're only going to have the work of the weight. And we have to see how far did the weight go down. And the weight went down. When you look, if we go from A to B, the vertical drop, according to the picture, was 15 feet. So again, the weight times delta Y. And it's going to be 15 pounds. And it dropped 15 feet. And once again, since that's has gone downward, then it's going to be positive. When remember we're working it with a work, it's going to be positive if it goes down to 25 pound-feet. And then the work of the friction. And remember, work of friction is always the friction force times the distance. And there's going to be the friction force, 3.6. And the distance it traveled, and that depends upon the path, right? That depends upon the path. And according to our picture over here, this was a 3, 4, 5 triangle. And you could double check this. This is saying that this would have been 25 feet because it's a 3, 4, 5. So if you look here, 3, 4, 5, if this was 15 feet, then this side would be 5 over 3 times 15, which is 25. This side would be, well, that one would be a little bit harder to calculate. You have to calculate this one from the 25. So this side is 20, excuse me, is 25 times 4 over 5. But the main side we need is this side here. And that relation is 3 to 5. So this is going to be 5/3 times 15, which is 25. So that's the distance that it experienced friction. And this is going to be negative because friction is always opposing the motion. And that gives us a negative 90. So I think we have everything we need to substitute in our equation. So again, T1, or in this case, we want to call it TA, summation of work from A to B, TB, like this. And this is going to be 1/2, 15, 32.2 VA squared plus 225 minus 90. That's the work here. And the TB was 463.5. And we get VA squared equal 1410.4. Then we take the square root of both sides. We get VA is 37. Let me just check that. 37.6 maybe feet per second. So again, we had to do this one backwards because we had to find the initial velocity. So we had to start at C, find out what we needed to get at B, use that to find out what we needed to get at A. Now let's take a look at this problem. A 2-pound brick slides down a smooth roof such that when it is at A, the velocity of 5 feet per second, determine the speed just before it leaves surface at B, and the distance from the wall where it strikes the ground and the speed at which it hits the ground. So let's take a look at this. One thing nice about this problem compared to the last one, there's no friction on the roof. So that'll make the part from A to B much easier. So let's take a look at that. So here we have the block, and we'll take the first part going from A to B because, and then we'll do the one from B to the ground. Now, since there's no friction here, when we do the second part, we actually could find go from A to the ground. So there's no friction on the roof, but we'll do it in these steps, A to B, then B to the ground. So from A to B, once again, let's do our kinetic energies. Say T1 is going to be 1/2 the mass, and this is a 2-pound brick. So divide by 32.2. And then the velocity is 5 feet per second at the start. And this comes out to be the first kinetic energy, or let me call the kinetic energy at A is 0.777. And the kinetic energy at B is 1/2 to 32.2. Now we don't know the velocity at B yet. So that's going to be just 1 over 32.2 velocity at B squared. And the only work that we have going from A to B will be the work of the weight. So it'll be the weight times the change in distance. And since it's going down, the work is going to be positive. And again, what did we have? 2 pounds. And then it's dropping 15 feet. So it's going to be 30. So then let's just put everything into our equation. Notice there was no other work being done, no friction work. There was no friction. Remember, this was smooth, no cable, no force applied. So we're going to just plug everything in. 0.777 plus 30 equals 1 over 32.2 VB squared. Excuse me. And the velocity is 31.48 feet per second when it reaches point B. Now let's do the same thing, find from B to the ground. Again, you could just put these into the equation if you want to. You don't have to go through these extra steps for these simple problems, but I just want to be sure that we keep in mind what we have. So we find the velocity at B to be 31.48. And if you put that in your calculator, divide by 3, this the kinetic energy at B is about 30.77 pound-feet. And then the kinetic energy when it reaches the ground, 1/2 to 32.2. Now we don't know the velocity at the ground. So it's going to be 132.2 velocity at the ground squared. And then the work done from the weight time changing. Hey, once again, it's going down, so that means it's going to do work, so it's going to be positive 2 pounds. Now this time, notice from B to the ground, it's 30 feet. So it's going to be 60 pound-feet. And put everything into your equation. B, the work from B to the ground. The ground, we have 30.77 plus 60 is equal 132.2 times VG squared. And if we put that in our calculator, it comes to around 54.06. You may want to call it, or 54.06 feet per second. So now to find how far it falls, you know, how what this distance D is, we're going to have to use the stuff we used from previous chapters. And so let's take a look at that. Mainly we'll go back here and see what happens when it leaves B. So we know at B, so B, the velocity was, we just calculated that to be 31.48 feet per second. And then we know that our triangle was a 3, 4, 5. Like this. And then that means if we want to find the x component, use x component here, which is going to be 4/5 times 31.48. If we want the y component, then you'd see it's going to be 3/5 31.48, like this. And 25.2 feet per second. $18.9 feet per second this way. So now we're going to have to find out how far the block travels. And so this goes back to stuff that we learned in the previous chapter. So we'll have to do like the our equation. So the equation for x is going to be like x naught plus v, the initial velocity in the x direction, plus 1/2 at squared. Now, like we always had before, we have no acceleration in the x direction because we're assuming there's no wind resistance. So we did this a lot previously. And you can consider this point right here to be the point 0, 0. And then so our starting x will be 0. And then the velocity in the x direction is 25.2 t, like this. And like we did in the previous chapter, we could then solve this for t. And that would be 25.2. This comes out to be about 0.04x. And we could eventually plug that into the y equation. So again, use your y equation that we did from a previous chapter. And again, if we're starting at 0, 0, this will be 0 here. Our y velocity is, and now notice it's going downward, negative 18.9 times t. And then negative g. This would be 32.2 t squared. And now we can substitute this equation into this equation. So sub t equals 0.04x into this. This will give us 18.9004x minus, and this is going to be what, 16.1004x squared. And if we put that in the calculator, we get negative 0.756. And over here, we get negative 0.2576. This. And now we want to find out, so now we want to find out when the ball, or when the brick hits the ground. And so again, it's falling 30 feet. So again, we call this 0, 0, and it's coming down like this. And it's going to go, now in this case, since we've called this 0, 0, this would be like negative 30 feet in this direction. And so we're going to put that over here, negative 30. Then we'll rearrange this. This will be 0.02576x squared, 0.756x minus 30 equals 0. And put that into our quadratic formula. And again, put this into our quadratic formula. Negative b plus or minus square root b squared minus 4 times a times c. Take the square root of that, divided by 2a. We get this, and then so this gives us one answer is 22.47 feet. And the other one is a negative answer, so we can ignore the negative one because that would indicate like sort of in time past. So this is going to be the distance. This will be the distance x or d, whatever you want to call it here, from the building. Now, this could have been done instead of doing this substitution, and I did it this way because this is the way we had done it previously. We found t in terms of x, substitute that into the y equation, and then this equation here will give us the position any point along the path once it leaves the B, and then we plugged in -30 where it's going to hit the ground, and then solve for x. Now, instead of doing this, you could have solved, you could have put, like, say, the -30 in here, and then solve for t, and then substituted t back into this equation to find x. That would have worked as well. Next, we'll take a look at this problem. We have a roller coaster, and it says it's designed so that the rider don't experience a normal force of more than 3.5 times their weight against the seat of the car. Determine the smallest rated curvature of the track at its lowest point if the car has a speed of 5 feet per second at the crest of the drop. So let's take a look at this problem. Again, so we're going to have to sort of work backwards a little bit in the fact that we have to start down at the bottom here at that 10-foot mark and find out what speed would be the maximum speed that we could have there so that we wouldn't have more than 3.5 times their weight against the seat of the car. So let's take a look at this problem. And so we have a picture like this. And so let's maybe focus down here and say the car is down here, and then it would have a certain weight, call it W, from the people and everything. Or we're actually, I guess, focusing on say on maybe one individual person. And so we don't want this normal reaction to be more than 3.5 times a person's weight. So we want NC to be, let's put that at 3.5 times their weight. Like that. Then if we sum the forces in the normal direction, again, we'll consider towards the center to be positive. So we'll have like NC minus their weight is going to be the mass, which is going to be 32.2 divided into their weight, and the velocity over rho, like this. This will be the equation we need to use. Now we know what this is, 3.5 W minus W equals W 32.2 velocity squared over rho. Now, one thing nice, all the W's are going to cancel. This will be like 2.5 W when we subtract these, but there's a W on this side, W on this side. So these will all cancel out. And we'll get 2.5 here. then when we calculate all of this and solve for v squared, we'll get v squared is equal to 80.5 rho. Now let's take a look at our work and energies again. So again, at 1, the kinetic energy will be 1/2 mv1 squared, which is 1/2 the weight divided by 32.2. And then the velocity at 1 is 5 squared. And that's going to be 0.3882 times W. And let's look at 0.2. It's going to be 1/2 mv2 squared, 1/2 W 32.2. And now here we can just put this in, 80.5 rho. And then we can simplify this to 1.25 W times rho like this. And then the only work we have is the work of the weight. And it's starting at the height of 120 and going down to 10. So it's a difference of 110 feet. I've been calling the weight W. And so it's 120 minus 10 is 110 W. Then we can put everything into our work energy equation. T1 plus a change in work is equal to T2. And let's substitute all of our stuff. 0.3882 W plus 110 W equals 1.25 W rho. And once again, what's nice here is all the W's will cancel. And so we get 110, 882 divided by 1.25, which is 88.3. Rho is 88.3 one, all right, we can probably do 88.3. So that's the minimum radius required so that they don't experience more than 3.5 times their weight when they get down to this bottom point.